Okay, so 5.3 again, as mentioned. So let's just go ahead and recall the two things, total change and average value. So the total change is pretty straightforward. So given a rate of change function, f of x, I keep saying total. They use the term net change, so maybe I should fall in line and use the same thing. But when I say total, I just mean net change. The net change is just from x equals a or t equals a, whatever you're using, to b, is given by just the integral from a to b of f of x dx. So nothing new there. The average value with all the same stipulations as above. Technically, it doesn't have to be a rate of change function for average value, so we can say, so the average value, which I'm thinking of as average height of f of x on some interval ab, is same thing, but you just have to throw the 1 over b minus a in front. And that's that. So let's go ahead and jump in some examples. I have the textbook opened here to the exercises from section 5.3. So I thought we'd just jump in there. Does this? Okay, so probably the best way is if I just use the snipping tool. And then I'll just copy the text in here into OneNote. So we'll say, what is this? 5.3, problem 16. Okay, so if we hop over here, we can just insert it right here. Okay, maybe we can make it a bit bigger too. Okay, so try to make it a touch bigger. All right, so that should be pretty good. So in this problem, we have a bacteria population starting with 400 bacteria and growing at a rate. So we have a rate of change function that's an exponential function in bacteria per hour. How many bacteria will there be after 3 hours? So what we do there is we just integrate from 0 to 3, and that gives the total bacteria. So yeah, they ask how many there will be, not what the increase is. So we're okay there. So the so yeah, the I just want to make sure, because it's just a little bit wordy whether you're thinking about the population increase or the actual total population. They're asking how many bacteria there will be after 3 hours. So let's go ahead and say the population increase in the first 3 hours is given by the integral from 0 to 3 of this exponential function, 450,268 times e to the 1.12567 t dt And we know to integrate that function, we're just dividing. It's the same function, but divided by the coefficient and the exponent, the 1.12567. Sometimes that's the problem with examples that try and use real data. The numbers get a little more complicated to work with by hand, so things are a little bit messier, but we can still get by. As mentioned before, you can always go ahead and check all this in Desmos. It's fairly easy to do numerical approximations of integrals. Okay, so then we divide by this 1.12567 number, and we're plugging in 0 and 3. So basically what we end up getting there is 11,713.23. That's when you plug in the 3, and then when you plug in 0, you end up getting just 400. And notice that 400 is actually just your initial population. So this is telling us what the population increase is, which is 11,313.23. So hence the total population after 3 hours is the initial population plus the increase, right, which was we're just adding the 400 back in because that was the initial population. So that's 11,713.23 bacteria. Maybe, again, this is a model, so it's not going to be, it's a bit of an estimation there, a projection. And having 0.23 bacteria doesn't make sense. So maybe you would just round this to the nearest whole number, 11,713. Anyhow, that's it for number 16. Pretty straightforward net change problem. They give you the function, you just have to do the integration work. Okay, let's do another example. This is number 29, but I don't need to clip anything to write it down. It's not too much stuff. So are there any questions on that one before I move on? No? All right. So let's move on. We're going to be doing, this is 5.3, number 29. So which is just a straightforward problem on doing a average value. So this one doesn't have any context or anything like that. It's just simply find the average value of the function. F of x equals 4x minus x squared on 0 to 4. So let's go ahead and do the steps. Remember, this is the one where we have to integrate, but we also have to do that 1 over b minus a in front of the integral. So here we have the average value is going to be 1 over 4 minus 0 times the integral from 0 to 4 of this 4x minus x squared dx. So we have 1/4, and then we can go ahead and do the antiderivative. So you add 1 to the power and then divide by that same number for each of these terms. These are polynomials, remember. So we're just using the power rule. So 4x squared over 2 is the same as 2x squared. And then we're going to have a minus x cubed over 3. Then this is from 0 to 4. And again, the nice thing about polynomials is when they have a 0, everything just goes away. So we don't even really need to worry about plugging that 0 in. So we have 1/4 times 2 times 4 squared. minus 4 to the third power over 3. And continuing with the arithmetic, this is 1/4 times 32 minus 64 over 3, which will simplify to 8 minus 16 over 3, or 8/3. Right, 8 itself is 24 over 3. So 24 minus 16 is 8. That's how we get the final thing there. So the average height of the function over that interval is 8/3. Yep. Not too much to say there. I was trying to think if there's a way we could graph them and discuss anything interesting. I mean, we could look at, say, Desmos again, and look at the graph y equals 4x minus x squared. And we're concerned with this graph between 0 and 4. So it just looks like this, the top part of the parabola that's cut off. So the only positive part of the parabola, the only part above the x-axis. And basically what we're saying is the average height of this is 8 over 3. So if we graph y equals 8 over 3, we get that. So one way to think about it is, let's say we threw in the two other lines that determine our starting and stopping point on the interval, x equals 0 and x equals 4. Another way to think about it, right, is if you reshape this into like a rectangle so that they have the same area, it would be exactly this rectangle where you have a base of 4 and you have a height of 8 over 3. And then those shaded areas would be the same. If that makes sense. Right, it's pretty easy to figure out too, right? Because if you have the integral from, if you wanted to find the area of the rectangle, you would just do 4 times 8 over 3, which would give you 32 over 3. And so we could check, I mean, again, it's pretty straightforward since we did integration along the way to prove that fact, but we could double check that the integral from 0 to 4 of 4x minus x squared is also 32 over 3. And so that's exactly what 10.6 repeating is. Because 30 over 3 is 10, and then the extra 2/3 is the 0.6 repeating. Okay, so the next one we want to look at is, how about number 30? So let's go ahead and look at the exercises 30 here. I don't understand why I can't. Oh, well. 30. Okay, so we're finding the average value of the function on the interval. So let's go ahead and do 30 and also do 32. So, yeah, h of t and a of v. Okay. So I think we can remember that. So example, find the average value of h of t equals 3.2 e to the 0.5t on 0 to 6. Well, so again, we're just really, I mean, we're not doing anything too interesting. We're just multiplying the integral by a fraction, but we're getting some practice with integration still, since it's still relatively new. So here, the average value is going to be 1 over 6 minus 0 times the integral from 0 to 6 of 3.2. Oh, I'm getting ahead of myself. I was going to write down the antiderivative. little high there. Let's write that lower. So 3.2 e to the 0.5 t dt. Again, this is a continuous exponential, so we're just going to be taking the same function and dividing it by 0.5. So we get 1 over 6 times 3.2 e to the 0.5 t divided by 0.5. And dividing by a half, as you know, is the same as multiplying by 2. So this is going to be essentially 1/6 times 6.4 e to the 0.5 t. And then we just plug in both those numbers and subtract them. And when you plug in 0, it's just going to be the 6.4. So plugging both these into your calculator and subtracting, you should end up with about 20.36. All right, so let's do the last one, number 32. So let's say example. Find the average value of A of V equals 4V minus 1 over V on 1 to 5. So what are we doing here? We're still doing the same thing. We're getting the fraction on the front, 1 over 5 minus 1 from our interval, and then we're integrating from 1 to 5. This function right here, 4V minus 1 over V dV. So again, the first one, 4V, is a polynomial, so we're just going to add 1 to the power of V and then divide by 2. But the second one, remember, the antiderivative of 1 over V is going to be the natural log of the absolute value of V. But because our interval is 1 to 5, it contains only positive numbers, we can dispense with the absolute value here and just write it as the natural log of V. We don't need to worry about all that. So this comes out to 1/4, and then we have our 2V squared minus the natural log of V from 1 to 5. Then again, you need to make sure you plug in things right. I mean, we can plug it in by hand. So we would have 1/4, and then we would have 2 times 5 squared minus the natural log of 5. And then we would subtract, and then we'd have to plug in 1. So that would be 2 times 1 squared minus the natural log of 1. But the natural log of 1 is actually just 0. So that's not going to be key. So what do we end up with here? We have 1/4. And then on the inside, we're going to have 50 minus the natural log of 5, and then just minus 2. So if you want 50 minus 2 is 48. 48 divided by 4 is going to be 12. So we have 12 minus the natural log of 5 over 4, which, if you approximate it, comes out to about 11.60. Okay, so are there any questions there?
Yeah, I have a question.
Yeah, what is it?
On the number we did above that,
Mm-hmm.
I put it into my calculator and I got a different number. I just want to make sure I put it into my calculator right.
All right.
For that one, we got 20.36.
Yeah, let me double check. Let me go grab my scientific calculator. I just had the number written down in my notes, but it's possible it's an error. So You may need to use parentheses in the exponent. I could see that as potentially being an issue. So let me just do both parts. So just to expand, this would be 1/6 times 6.4 e, and then if you plug in 6, 0.5 times 6 is 3, right? So we just get e cubed minus 6.4 because e to the 0 is 1. So this is essentially what we're doing. So 6.4 e to the third minus 6.4 is 122 something divided by 6. And yeah, I get exactly 20.36. So maybe if you tried to do it all in one step, my guess as to what you did wrong is probably you did something like 1/6, 6.4 e 0.5 times 3, something like that, minus 6.4 e to the 0.5 times 0, right? You did something like this, and then you just tried to type it all in at once.
No, I just so my calculator I put 1/6 and then I put in parentheses 6.4 e to the 0.5 and then I put in parentheses the 6 and then I put in the last parentheses and I got 21.42.
21.42. So why don't you do each part separately, and we'll try and parse it out from there, right? Because we're let's do each one of these numbers. If you try and do everything in at once, it can. I don't know where your error is going to be just because I can't see what you're typing. But if you do 6.4 e to the 0.5 times 6, that number should be something like 128.547. And your other number should just be 6.4.
Okay.
Right. And then if you type that into your calculator and press equals, you should get 20.36.
Okay, I got it.
Yeah. So, I mean, I probably you're just trying to do too many steps at once in your calculator, and it's difficult to see where your mistake is. So, so this is a calculator question. I mean, the syntax tends to, increase rapidly as you have more and more sets of parentheses and exponents. So at some point, it's either a keystroke error or something like that. So if you're confused, normally what I suggest you do is just do many parts of it and then combine. So just break it down into a few more steps. Again, we can always go back to try and get the right answer by to confirm that we're right by just going back into our Desmos and say we could set up the integral. So the integral from, sorry, I'll write down which one this was. So actually we want the 1/6 in front, right? So 1/6. Then we're integrating from 0 to 6, 3.2 e to the 0.5 t et. And we see we get the same answer that we had written down. So that's another way to, just double check if you're not convinced of something that you're typing into your calculator, for whatever that's worth. Does anyone have any other questions? No. Okay. Well, let's try and find maybe one or two more exercises. Because I want to wait for Friday to do the homework. I don't want to kind of split that up into 2 different days. But like I said, this is kind of a short section, so there's not too much to do. So we'll just try and find another problem or two. So I don't know what looks interesting. This one I do a lot. I've included on test before, number 33, so it's probably a good one to look at. It's a average problem or whatever, an average value problem, but it's a word problem in this case, not just a function. So let's take a look at this. So this is 5.3 problem 33. Okay. So come down here and insert this. I hate how that pop-up happens right there. Okay, that's probably big enough to see. So we've got a function that's measuring the temperature in a city in Fahrenheit, T hours after 9 a.m. So what we want to do is find the average temperature during the period. So we want to think about, so since T is hours after 9, that makes 9 a.m. That corresponds to T equals 0. And 9 p.m., the other object in question, would be T equals 12, right? It's exactly 12 hours later. So that's what we're going to use for the interval that we're doing. So to get the average value, we would say, okay, the average temp, this would be the 1 over 12 minus 0, which is just 1 over 12. And then we integrate from 0 to 12. Whoops. And then we have this polynomial. So the integration should be easy. But again, like I said, since this is probably some actual data, the formula is a little complicated. Okay, so we have our integration set up. So again, we're going to have 1/12. And then remember, this is a polynomial. So the first term you add t to, then the next one you add 1 to the exponent, divide by 2. The next one add 1 to the exponent, divide by 3. And the last term add 1 to the exponent and divide by 4. So we have 57t minus 2.4t squared over 2. 2.4 over 2 is just 1.2. 0.43 over 3 is probably not so nice. So I'm going to leave it like that, and same with the last one, 0.014 t to the fourth over 4. Now, it's not super difficult to plug in here just because, again, remember when you plug in 0, all of these terms now have a t. So plugging in 0, everything just goes away. So really we just need to plug in that number 12 here. So we have 1 over 12, and we're just plugging in 12 for all of these t's. And we'll see what happens with the answer. Again, for a lot of these, this is a question about temperature, a word problem, so we should have some indication of whether or not the answer seems reasonable. If it doesn't seem reasonable, it's always worth going back and double checking to make sure that you did everything correct, or seeing if you can find any kind of errors. So I'm just typing it into my calculator now. Should be a minus. Oops, I keep 0.014 times 12 to the fourth divided by 4. Okay, so I got an answer of 57.192. And that would be degrees Fahrenheit. Let's look at the problem to see if it tells us a location. in a certain city. Yeah, it would be nice if we actually knew what the city happened to be. But this is number 33. There's two ways of checking your answer. You could either go to Desmos and do the integral like we've been doing. I think in the book, though, for odd exercises, it gives answers. So I don't know how difficult that would be to find. Appendices, maybe. Answers to odd number exercises, and we want 5.3. Probably let's jump ahead to like A 65. A little too far, maybe A 60. Okay, so there we go. 5.3, 33. We got 57.2. So we got exactly the right answer. I mean, they rounded to one decimal place. Ours is a bit more, didn't round as much, but for all intents and purposes, that's the answer. Any questions on this problem? Just ends up you're integrating a polynomial, so a bit easier than some of the other ones. Okay, let's see if we can find maybe one more exercise to look at today. So we got to go back to 5.3. Maybe it's better to go to 5.4 and then go backwards. So we did 33. This one's a cup of coffee. That's cooling again. Investment balance. Compute the average balance of the account during the first 5 years. Show concentration. Yeah, they're all with exponential functions. Nothing too tricky. Why don't we just do 36, and then that'll be it. So 5, 3, 6. Okay, so that's good enough. Again, this is not too difficult. Just another basic integration problem. So the average balance here. The interval, it just tells us during the first 5 years. So that just means we're going to do 1 over 5 minus 0, which is 1 over 5, and then integrate from 0 to 5, the value of this account. As you might recall from exponential functions, this one's in continuous form. We can see it's earning a continuous rate of 6.2% interest in that account. So the integration, again, is going to be simple. We just do the 48,000 divided by the 0.062. Another thing you can do is you can actually pull the 48,000 all the way in front and then just integrate the e to the 0.062. So, I mean, you can actually rewrite it that way. Right, you could do 48,000 over 5 and then just integrate the exponential part. Maybe that would simplify things for some people. So e to the 0.062t divided by 0.062 from 0 to 5. And then, I mean, the only reason that's kind of nice is 48,000 is divisible by 5 is one of the reasons you might think to do it. So this is 9,600. And then we've got this e to the 0.062 times 5 over 0.062 minus e to the 0 over 0.062. And then we should get our answer right here. So 9,600 times e to the Okay, so we end up with an average balance in this account of 56,272.28. So pretty straightforward. Again, like I said, there's not much to this section. It's just a lot of practice rehashing basic integration techniques using these two formulas. So is there any questions for me here? Okay, then I'll go ahead and end the recording.